Okay, welcome to one more video on binary multipliers. In this video we'll see how do we design a digital circuit to multiply two binary numbers. So we know that multiplication is nothing but a repeated addition. Suppose assume that we have uh, two 4-bit numbers which need to be multiplied. So let us consider it like, okay, so I need to multiply 14 by 15. So I'm going to call this we're going to have multiplicand and multiplier. So if I say this as my multiplicand, and this will be the multiplier. So this is the multiplicand and multipliers. So we can write its binary values. So my multiplicand is 1 1 1 0, so multiplied by the multiplier is 1 1 1 1. So this is how you can do the multiplier and multiplicand in its binary representation. So since we know that whenever you have multiplier all bits as 1, multiplier bit is 1, we simply add the multiplicands. So in this particular case, since 15 all bits are 1, so let us take a different example. Maybe 14 into 12 would be fine. Suppose if I take 14 and 12, it's again the multiplicand is 1 1 1 0, the multiplier is 1 0. Okay, this is 1 0, it will be for 12 it is 1 1 0 0. So 1 1 0 0 would be the number, or let us make it as 13. So for 13 it is now 1 1 1 0 multiplied by 1 1 0 1. So this would be fine. So I need to get the multiplication of 14 and 13. So in order to get the multiplication of 14 and 13, so since you can see there is a multiplier with bit 1, so let me add the multiplicand. Okay, let me retain the multiplicand what I have. So this is my multiplicand. There is a 0 here. Since it is 0, so I will not add the multiplicand, but I will add zeros to it. So I will add zeros, and you can see there is a multiplier which is 1, so I need to add the multiplicand. Whenever I'm adding the multiplicand to the partial product which is already obtained due to my previous bits, I want to shift by 1 bit towards the left side. So it is now since I want to add the multiplicand, it is now 0 1 1 1. Of course you can append the zeros here, because if you add zeros there will be no change in the values. And we are done with first multiplier, which is bit 1. This is 0, all zeros are added, again 1, you are adding the multiplicand. There is one more bit 1 in the multiplier, so I need to add the multiplicand here. It is now, this is my values, so I can now get the complete value. This is how manually we can add it. So this is 0 1, and you can see this is again 1. It is 1 plus 1 with a carry 1. Okay, now there's a carry now. It is 1 with a carry 1, and it is again 1 with a carry 1, and it is 0 with a carry 1. So we have this as the value of our multiplier, which is we have it as 13 into 14, which happens to be 182. So I want to have this 182 as my number. If I can actually find out the decimal equivalent of this binary number, so this exactly comes out to be 182. So now let us see, okay, this is how we manually do the multiplication of two numbers by considering the multiplier and multiplicand. If your multiplier is 1, you add the multiplicand. If multiplier bit is 0, you simply shift it by 1 bit. This is the idea behind realizing a binary multiplier. Let us try to identify, okay, how do we realize this in hardware for a digital circuit. So let us consider the same example whatever we had now. So now again let us go with this number whatever we have. The multiplicand is 1110, which is 14, and the multiplier is 13, which is 1101. we know that okay, we are supposed to get the first bit would be whatever multiply you had, so that should be ANDed with multiplicand. Suppose if this is equal to 1, I will get as it is irrespective of the value of your multiplicand. So suppose if I consider this as okay, b0, b1, b2, b3, and this is like okay, a0, a1, a2, a3. So first what we can think of having is, so you can AND a0 and sorry b0 with all other bits. So since it is b0 is 1, so ANDing of this with a0, a1, a2, a3 will be same as a0, a1, a2, a3, because ANDing of that will be same as the multiplicand. So I will retain it as 0, 1, 1, 1. Okay, this I'm getting because of the ANDing of b0 and b0 with a0, a1, a2. So you can just think of having let me start writing it simultaneously. So this is my AND gate, so this is again my AND gate, and this is my third AND gate, this is the fourth AND gate. For all of them, one of the input is common, which is coming from my b0, which is coming from my b0. The other input is coming from, this is my a0, this is a1, this is a2, this is a3. Because as we saw here, this was my final output, so this happens to be the LSB of my the product. So if you say this is m of 0, the entire product, so okay, let me just say it as product 0, p of 0. So this is what I'm getting directly from the AND of operation. So we are done with, so this is one partial product what you have. So let me say it as okay, some value, and I have to consider the next bit. So next bit what I have is now let me just consider the b1. So I will consider b1. So when I consider b1, so let me consider b1 bit, and okay, now this b1 bit and consider. So now okay, this is done now. So with b1 what we have, okay, b1 a0. So okay, since b1 is actually 0 what you have, so now it is now 0, b1 and with a0, and b1 and with a1, b1 and with a2, and then b1 and with, so this is now a3. So this is b1. You again use this as one of the input for your AND gate. So let me have the AND gate now here. So there is one more AND gate, and there is one more AND gate. I got the fourth AND gate. So one of the input is coming from b1. The other input what I have is now of a0, a1, a2, this is a3, and I have my these things. See now now in this case what I have is something like this. So actually here what we did was we simply added these two numbers. So it is 1 plus 0, it is 1. But how do you actually add this 1 and 0? This is actually 2 bits you are adding. For adding 2 bits, I actually need a half adder. So this is a half adder. So I need to have a half adder which is adding what partial product of my previous output and the present partial product, that is ANDing of a0 with b1. So I need to have a half adder now. So there is a half adder required to get this intermediate answer, which is now 1 1 1 0. Even though it is 1 1 1 0, because you have it as 0, in order to get this answer I need to have a half adder here, because it has got only 2 operands. Since we know that this half adder, suppose if there was a 1, it was 1 plus 1, which is a sum 0, and there is a carry coming, so there is a carry also generated because of this half adder. So I'll be having the third input for this particular sum, so I need to have a full adder here. So I need to have a full adder to get the sum of this, because there is a possibility of carry coming from this. So what I'll do, the two inputs for the half adder is, one is this, the other one is this, and whatever sum you get will be the final answer, which is P1, the second LSB of your the final product. So we know that there is a sum coming up. So there is a, this is some part of it, this is carry part of it. This carry which is coming from the previous half adder and the full adder. So what are the two inputs for the full adder? One is coming from the top and other one is from this one. So I'll have a full adder now. So the three inputs for the full adder is, one is from this, the other one is from this. This is my Cn. You can see I have the sum here. Of course, this is my final sum. Okay, this is okay. Now here also there is a carry that is generated. There is a carry that is generated which will be used for this addition. So again you need to have a full adder. It's a full adder required now. So I will take one more full adder. The three inputs for this is a carry from the previous full adder. There is one from this AND gate and there is one more from this AND gate. There is a carry coming and you have only one input coming from this AND gate and there is one here. Just a half adder is enough. Just a half adder is enough. Here you have the sum, you have a carry. So this is carry, you have a sum. So the carry of this full adder, this half adder have been used for the subsequent full adder, half adder. This carry is still left out because whatever carry that you may get out of these two will be just used for next bit. So we are done with B0, B1. Next I will go with B2. B2, and then it is ANDed with, it's ANDed with, okay, I will take this one, this one, this one, this one. So B2 with A0, B2 with A1, B2 with A2, and B2 with A3. You can see these are the AND gate outputs. See now, you have the sum which is generated in the previous case will be used as one of the input, of course. Now, so let me rewrite now here. So this was my final thing. So you have a 1 now. So since it is 1, I need to consider the multiplicand as it is. So what is multiplicand? It is 0, 1, 1, 1. So now have a 0, 1, 1, 1. You can see now this, because it has got only two inputs, one from this AND gate and the previous sum. So this happens to be half adder. There is a sum coming up and there is a carry. So since I got this as well as the carry of this, I will have a full adder. Sorry, I'll have a full adder now. These are the three inputs for the full adder. There is a carry generated here which will be used for the next full adder, this one, and then you can see this is also coming, and then fine. Now you have, see now this is one of the input. The carry which was there generated in the previous half adder will also be used as one of the input for this, and this is again the other input. You have actually three inputs for this full adder. That's why you need to have a full adder. In the previous case you had half adder, two full adders followed by half adder, but here in the third case, second stage, you have half adder and three full adders. This is again a carry. You have some, some. This is A0, sorry, B0, B1, B2. Then last one is, of course, this is your P2, of course, P1. Let me just write the last one. This is your B3, which is now ANDed with this. Again, this is ANDed with this. This is ANDed with this. I want to have one more AND. So this is AND of B3 with A0, B3 with A1, B3 with A2, B3 with A3. Since we have these sums which are coming from here, and this is the final carry whatever you have. So what we'll have is one half adder for this, which is taking this input and this input, and of course there is a sum generated here, which is now P3 happens to be. There is a carry that is generated because we are almost at the end of the fourth multiplicand. So I will going to have one more full adder. The inputs are this AND gate, this sum of the previous full adder, this is my carry, this is my sum, there is a carry coming up, and this carry is one of the input for the full adder, and the other two inputs are this. And then over here you have one more full adder. The carry is coming from this, and the carry from the previous thing will be this. So you can see now you have P0, P1, P2, P3, P4, P5, P6, P7. So P0 to P7, that is 8-bit binary output would be the product of this particular thing. Of course it just continues this way what you have. So then you have this is coming down here, then you have it as 1. This is now 1 plus 1 is 0, it is 0, then it is 0 with a carry 1. Then you have one more 1 now, so this will go down here. Since you have one more 1, the multiplicand is 0, 1, 1, 1. Suppose if you add this, this will be okay. The final answer would be, so you're going to have it as because this is 0, 1, 1, 0. This is again 1 here, 0 with a carry 1. So this is what you have now: 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1. So this is what P0, P1, P2, P3, P4, P5, P6, P7. So P7, they're actually 8-bit binary output. So this is how we can able to get the output from a multiplier using the half adder full adder combination for generating the partial products. Of course, for partial products are generated by having the AND gate and the half adder and full adders, and then finally you are getting the full the product output, which is a 8-bit value. So you can see it's a complex circuit when you have, suppose if the number of bits are more, supposing that you have 32-bit into 32-bit multiplication, so then you need to have, you can just imagine the complexity that is there associated with this particular thing. So it always boils down to what is the amount of time that is required to generate a multiplier or a multiplication of 2 bits is. So it depends on how many times you're going to add. So whenever you are adding, you can see the carry has to propagate all the time. So we'll see in the next video, so in what all way we can able to reduce the time that is required to generate this multiplication, because as long as your multiplier is 1, you're supposed to add it, because for each and every combination, assume that in this case of 1, 1, 1, you're supposed to add the multiplicand every time and shift it, because adding and shifting has to keep on happening. Suppose if you minimize the number of additions for a given multiplier, then you can able to somehow reduce the time that is required for getting the product. So it's always, we are supposed to find out some methodology where I can able to reduce the number of additions so that I can able to reduce the overall time that is required to get the final product output, because shifting may take just only one clock cycle, whereas the addition will take multiple clock cycles, because the carry has to ripple through the n number of bits. So we'll see one such topology where we can able to reduce the number of additions depending on the multiplier value.